Welcome to homework.
Let's step through what reagents we would need to generate the following. A and C, I'm going to group together, right? Chlorobenzene is generated with chlorine gas and AlCl3, whereas bromobenzene is generated with bromine gas and iron bromide. Right? They're very similar reactions, which is why I'm grouping them together. Okay, so what about nitrobenzene? This is kind of a weird one, but recall that it is the H2SO4 and HNO3. That's sulfuric acid and nitric acid, which will generate nitrobenzene. Okay, what about ethylbenzene? Well, we can kind of group this with some other ones, but there's a caveat. So recall that to add any R group, we simply need, say, a chloroalkane with that R group represented, and aluminum chloride, right? And this will work for ethyl, right? This is totally fine for ethyl. This will generate ethylbenzene. Okay. There's an issue, however, if we get to larger groups, right? And this will come up in a bit. For example, when we look at E, this is an example of what will not work. We want propylbenzene, which I assume is N-propylbenzene, so a straight chain, right? If we react this with aluminum chloride and benzene, we will not get propylbenzene. We will instead, due to carbocation rearrangement, get isopropylbenzene. Right? And the reason is that effectively what we're doing is generating a carbocation here after this complexes with the aluminum chloride. And then we'll see a migration of this proton to generate the actual reactive intermediate, which is this isopropyl cation. Right? So when it comes to alkanes adding to benzene, you've got to be careful. You can't just use aluminum chloride and a chloroalkane. If there's going to be, see, in this case, if we generate a carbocation here, it's equivalent to a carbocation there, right? That's not true for, in the case of the propyl, this carbon would be primary and this is secondary, right? So that's why it does work for ethyl or methyl. Okay. Right. So for propylbenzene, we've got to do something else, right? And the solution to that is Friedel-Crafts acylation instead of Friedel-Crafts alkylation. And that is, we create the carbon chain that we want, but we make it an acid chloride, right? And we react with aluminum chloride. Because now what's going to add is this. There'll be no carbocation rearrangement. Recall. And the final step then is to reduce this carbonyl into hydrogens, right? Right, and now we've got our N-propyl group just like we wanted. And typically this is done with a zinc in mercury amalgam in HCl. Great. So that would be the answer for E. Now we can move on to F. F we have actually already seen. This was just starting with 2-chloropropane and AlCl3 because there's no non-favorable right? If we generate a carbocation here, it's not going to move into being primary, right? It's going to remain secondary, right? So that's not a problem. Okay. Next is aniline. So aniline is actually the same as making nitrobenzene, we just reduce it afterward, right? So we're still going to want the H2SO4 and HNO3. We're making a nitrobenzene, but then with reduction using H2 or palladium, we will convert that, right? Remember, a nitro group is just a very oxidized basically an oxidized amine, and we just reduce it into an amine. Right. So that's the path to aniline. Okay. Next, we've got benzoic acid. I'm going to couple this. I'm going to come back to benzoic acid. I'm going to do toluene first, right? Toluene is simple. It's methyl chloride, right, and AlCl3, right? And that will generate toluene. It's just adding a methyl group. That's toluene. Benzene with the methyl group. Well, if we then use, we can actually oxidize this methyl group into a carboxylic acid, just using potassium permanganate. And that will generate benzoic acid. Right? So this is I, but J is doing I and following it up with H, I should say, H. Benzoic acid is to generate toluene and then oxidize it with potassium